Okay, so this is my second attempt at making a video because my first one somehow disappeared. I think the internet gremlins ate it. All right, here we go. We're going to have to do a quick refresher on a couple things we talked about in a previous module. We talked about relations, okay? And then we interpreted the graphs of those relations, and then we talk about appropriate scales. We learned about what a relation actually was. It's a pairing of numbers, x and y, one domain with one range, exactly made a function. We talked about how we were able to show different ways of functions, whether it be with mapping, with graphing, with table, or with equation. We just spent the last week or two graphing functions from data from a table, slope-intercept form, and then we put them all in a graph. So we were able to describe ways to show our relations, order pairs and whatnot, being a table, a graph, and we map them. Then we also interpreted different graphs. Okay, we talked about independent variables, which is our x's, and dependent variables, which is our y's. Independent variables down here, dependent variables over there, right? So that's important to remember when we're talking about this next. We did a little bit of functions too someplace. Functions. Yep, here's some functions too. So in talking about functions, we talked about the domain and the range and how it has exactly one input matches one output. So when we're dealing with our function, we have one domain with one range. Remember, -6 can't be hanging out with 0 and with 8. Not a good match, right? It's not going to work. Our functions have to pass the vertical line test. This one does. This one, bonk, 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 does not. So it identified functions, we deal with relations. Now we're going to go jumping ahead into something called understanding the linearity and continuity of graphs. We're going to look at graphs a little bit better. So we have to keep in mind our domains and our ranges, our inputs and our outputs, and how that impacts what the graph looks like. So for example, we're going to deal with discrete and continuous functions. Yes, you're going to take a look at some graphs that have a certain set of inputs or a certain set of independent values. Those are our domains. The outputs will also be specific to that, and that's going to be a set of range values. They're individual values. They're not going to be a continuous flow. In this case, here's their continuous flow. The points are connected to form a line or a curve. We've been graphing lines all the way along here. We'll be graphing curves next. And so when you're dealing with curves or lines, understand that the domains are all real numbers because they put any number in. Let's see if this will work. And our ranges are going to be also continuous. There'll be an interval of range numbers. So for example, when I'm looking at this with my domains and my ranges, understand that the big concept that you're going to have is my range, for example, can't go past that -4.5 or that -5. I can't go down here. I can't pick a -10 for my range to maybe. I cannot include a -10. However, for my domain, I can include any values here along the x-axis. Here, for our continuous or discrete, they're neither continuous or discrete. We can't have our domain be in this region, right? We can't have it be 0, 0 for a domain and for a range. Our domain cannot include a -9. Our domain cannot include a -7. It could include, it can include a -9. It can include a -7. It cannot include a -4. Any numbers through here cannot include 0. So that this means that the graph means that I'm able to include certain parts that are on that graph. Okay, if it's not on that graph, I can't include it in our domain and our range. So in this graph here, if I'm looking at the book bargain barn, we're noticing that if I have a certain function, they want to know if this is a continuous or discrete function. If I'm looking at this, I have a number of book. Here's my price: 2 books, $2.90; 3 books, $4.30; 4 books, $5.70; 5 books. So you go to those places, they have a general rate for some books. Certain books cost a certain amount of money. You can graph that number of books, and here's our dollars that we're going to spend. So when looking at that, I don't buy a half a book. I only buy 1 book or 2 books or 3 books. I'm not going to buy a half a book. So this is going to be considered a discrete graph. If you look at our issues of a discrete graph, our discrete graph, the points are not connected. It's a discrete function, and the domain has individual values, and the range also has individual values. So in looking at that graph, you'll notice that the domain and range would be considered as they call it just essentially, I'd say the domain would be the set of all positive integers. Because I could pick 1, 2, 3, 4, but I wouldn't be picking any decimals. And then the range, obviously, the set of positive integers as well. I just write that out, positive integers. Now, if I'm looking at this here, they want you to determine if it's continuous, discrete, or neither. Here's our different functions. Well, obviously, I'm flowing through. I do not pick my pencil up. That is going to be continuous. Here, I have to pick my pencil up to plot the graphs. That's going to be discrete. And then when I go talk about the domains and ranges, I go back to my original chart. If I'm looking at not continuous, not discrete, my domain values and range values will vary. If I'm looking at continuous, there'll obviously be a certain interval. So here, I could say that I have all real numbers, and it looks like my domain will also be all real numbers as well. For range and domain, I can pick anything here and anything here, and this is going to somehow hit both of those guys. Do the check on your own. Take a look at example number 3. Example number 3, they want to know if this function model is discrete, continuous, or neither. Well, I'm just taking a look at this particular graph. That's certainly not going to be continuous. Okay, it certainly is not going to be continuous. So then, what other criteria does it match? Well, my points are all individual. Okay, it's definitely not continuous. Can't be drawn with a straight line, or it's not a curvy thing. It's not a line or a curve. So essentially, it's neither continuous nor is it discrete. So it's one of those really weird kind of graphs that just can't be called one thing or the other. Oh my gosh, just take a look at that one. Is it discrete, continuous, or neither? Put your finger down here, trace over it. Did it come up at all? Nope, it did not. Therefore, it's continuous. Take a look at this next one right here. The linear function, or linear and non-linear function. Well, for some reason, I can't get my stupid color to change. I want it to be the nice neon blue. Oh, there it is. Yeah. Ha! Okay, good. It's like going to the car dealer, the car repair mechanic, and your car's making that noise, and then you bring it to the mechanic, and that's not making the noise. Make that the phrase that pays. Mechanic noise, mechanic car noise. So we'll know. Listen to my story. Okay, mechanic noise on page, what page is this? 160, page 160. Mechanic noise. I'll write that down so I don't forget, because I will. Okay, here we go. Important to note the linear function has a graph that's a line. We've been doing that all the way along, okay? They called the term linear equation to describe the type of equation that makes a linear function. When you've been doing it, when we have our ax plus by equals c, when I have, the 3x plus 2y equals 15, you get to graph that. That's in standard form. Slope-intercept form is the y equals mx plus b. This is our y equals mx plus b. That's slope-intercept form, okay? You can rewrite that in a standard form. Now, if I have a nonlinear function, okay, nonlinear means it's, guess what, not in a line. You cannot use that to represent it. Don't forget, when I'm writing my lines, my functions or the equations in standard form, it's a cannot be 0. It has to be bigger than, it could be 0, but it has to be 0 or greater. Oh, actually, that is really weird. It says a cannot be greater or equal to 0, or both a and b are not. Okay, not 0. Oh, it seems so weird to me that they write it like that. Essentially, if it is 0, don't forget, then you could have a certain type of line, whether it's horizontal or vertical. Interesting. Okay. So in this example here, I have a 2x plus 5y equals 7. A is 2, b is 5, and c is 7. So just know that this is the number in front of the variable. So if you actually have a linear equation, it can be written in the standard form. Is this in standard form? Well, you could go ahead and try and simplify that, and you'll see what they did is they simplified this. Oh boy, let me change my pen. Too thick here. Okay, and if I were to do that, hang on one second. Okay, I just checked my mistake. This is 2 times x. That quantity is squared. I did not pay attention to that. Bad dot m. So I get 4x squared. Well, 4x squared minus 4x squared is 0. They're trying to do some trickery and tomfoolery with you guys. So when you actually simplify it, yes, indeed, I do not have any squared, so that's good. So now I'll go further just to see if I could make sure I could rewrite this in standard form. To rewrite this in standard form, then I have to have AX plus BY equal to C be my format. Right now it's in slope-intercept form. So now they'll do the math to get it in standard form. So when they do that, they went ahead and subtracted 3x from both sides. You can't have, they don't want you to have a to be negative. If you remember, when we're dealing by standard form, a is greater than or equal to 0, so a has got to be positive. So that first term of x can't be negative for it to be in standard form. And so essentially, they multiplied everything here by -1 because they did not want to have to be in standard form. They want it to be in standard form. Now, go, ooh, this looks fun. Let's do this check here. And I want you to do that check on your own. Be especially careful about this guy right there. Okay, we'll do that in class. We'll check that in class. Okay. You have to identify linear and nonlinear functions. You have to tell if it's linear or nonlinear. So really, they want you to do, they want you to simplify these different functions and see if they are can be written in standard form. Okay, I'm not a big fan of fill in the blanks, so I just did it off to the side. I combined my like terms, and I have y equals 4x cubed plus 3x plus 6. I don't think there's any way I could do anything about that right now. Oh, I wrote the problem down wrong. That should be, this is minus, sorry. 2x cubed plus 3x plus 6. You can't do anything with that. I can't combine any more like terms other than that. I found my mistake over there. Even with the 4, it's still a problem. The 2 is still a problem. I cannot simplify that because of this power of 2. Okay, so it's not going to be a line. In other words, it's not a linear function. Go ahead and do the check. We'll check that on our next class period. Hit pause, and now we'll talk about number 6 when you get back. Okay, welcome back. You take a look at example number 6, and go ahead and read that problem. All right, so they want to know if it's linear or nonlinear. Well, I'm just looking at this right now. I'm going up at a consistent by 5-second intervals, right? Which is, no big deal. Or half-second intervals. So I'm looking at that. That's fine. That's a constant rate. But with this guy here, from 2 to 28 is 26. From 28 to 46 is 18. Oh my gosh. Then 46 to 56 is 10. So this is going to be 2. So I'm looking, and then we're going down. Therefore, it's not a consistent rate. I don't care what this other stuff says. It's not a consistent rate. I don't have a consistent slope. It's not a linear function. It's also not consistently going up or down, so it's not a curve. So I'm going to go with, since my change in height is going to be changing, it's increasing, then decreasing. This is not a linear function. Go ahead and do the check, and we'll talk about that in class. Press pause and do it. Okay, example number 7, Fernando. Okay, so I checked out Fernando. If I look at this table, it's going up by 5s here for my minutes, for my time. That's going up by 60 gallons each time. So for a plot, that's definitely a line. Yes. Now, I would consider this to be a continuous graph because our time could be in tinier intervals than other than 5 minutes. It could be 1 minute, it could be 30 seconds. It could be, we have very fluid ways of measuring time. So technically speaking, for all intents and purposes, this could definitely be considered a continuous linear graph. I can understand the argument where you could say it's not continuous because the amount of measure are listed in the times. I could see, just put the dots in it because you only have the times there. But I understand you're filling this at a constant rate. So because water is kind of a fluid thing, it's measured. We have the very tiny units of measuring it. I do think that we could consider this to be a continuous line. Go ahead and do the check. We'll talk about that in class. And that will be the end of this video. Make sure you do the check.